Hi, I'm Ben Goertzel. I'm the CEO of SingularityNet, a blockchain-based platform for decentralizing AI. Also the CEO of True AGI, a company working on artificial general intelligence technology, both as an R&D project and as a way of creating better and better enterprise software. And I lead the OpenCog Foundation, which is behind the OpenCog AI project, which is a open source toolkit aimed at artificial general intelligence. I've been doing AI since the 1980s through a whole bunch of different AI paradigms. There's never been a more exciting time to be working on artificial intelligence. That's for sure. So what I want to talk a bit about today is large language models, which are sort of the hottest thing in the AI field now, and some of their limitations and how we can sort of work around those limitations by doing various fancy tricks and then by integrating them with other sorts of AI. So that will be fairly high level. I'm not going to be going over code details, but there are code details, of course, underlying all of this, which done and is being done with open source code. So this is all stuff that you can plunge into right now as an open source developer, and I'll give some pointers for where to look if you want to dive right in. Large language models, these are revolutionary in many respects. I think probably by integrating them with other IT systems out there, you could obsolete a considerable majority of jobs that people now get paid to do. On the other hand, they're still reasonably far short of what you think of as human level general intelligence. So the notion of AGI, artificial general intelligence, is AI programs that can take big leaps beyond their training data and beyond their initial programming. And large language models don't really do that. They're not exactly classic narrow AIs. I mean, a classic narrow AI system does one little thing, like do your taxes or play a chess game. Large language models are narrow in a sense, but it's a strange sense. Like they're narrow in that they can't leap too far beyond the data they've been trained on. On the other hand, they've been trained on the whole web, so they still appear broad compared to the scope of an individual human mind, even though they're not able to go too far beyond their training. But they have a few key shortcomings that I'll just allude to briefly now and then step through some of them in more detail afterwards. So they're not good at complex multi-step reasoning like you have to do in science or math or engineering or political strategy, let's say. Their creativity is generally derivative and banal, just making sort of shallow combinations of things that they've seen before, rather than making a big creative leap like, say, Duke Ellington or Jimi Hendrix or Picasso did, or James Joyce or something, right? And these limitations are rooted in the fact that they're not autonomous agents sort of making their own decisions as they navigate their lives in a world. I mean, I think if you go into the cognitive science of it, a lot of the ways we do complex multi-stage reasoning, these are grounded in our planning in our everyday lives as an agent, and the creativity that we do is based on representing the source material for our creative combinations in terms of what's meaningful to us in our lives. So not being agents controlling themselves in a world, but just being answering systems, I think is related to the issues that LLMs have with multi-step reasoning and creativity. These are limitations that, in the big picture, I think we can work around by putting LLMs together with different AIs from different paradigms, like reasoning engines or evolutionary learning systems. But in the short run, we can partly work around some of these limitations by various other clever tricks, and I'm going to talk about some of those. So let me share my screen here. So yeah, I'm going to talk, among other topics, as you see in the title here, about putting LLMs together with other sorts of AI methods like symbolic reasoning or evolutionary learning. Examples. Example, have an expiry date, because what GPT-4 or Llama 2 is dumb at right now, after a little fine-tuning or upgrading, it's not dumb at that particular thing, but the qualitative phenomena illustrated by these examples are not going away in the immediate term. So here's a sort of funny case. You ask, in this case, it's GPT-4, ask it to multiply two numbers. Okay, it can do it. I don't know how, probably invokes a calculator. Then you ask it to factor the result, but it does something wrong, right? It comes up with the wrong factorization instead of just multiplying the two numbers that you told it to multiply to get that number in the first place, which is quite funny because it doesn't know what it's doing in a basic sense, right? Like it doesn't connect your current query to the previous query, even though in a way it should know how to do that. Another fun example. So it doesn't recognize the letter H as ASCII, or hello says great, it just makes up. On the other hand, if you ask it to draw ASCII art, it can draw the word hello. So it's like its perception and its action are out of balance, which is funny. It's not what would ever happen in a system that evolves perception and action together to control an agent in a world, right? It's a result of the strange way that it comes by its perception action capabilities. And you can evaluate these limitations rigorously. Look at something called the step game. So you give simple graphs and you kind of explain the graphs in words, and you ask questions like, what's the relation between the G node and the J node? And it's very simple. Like the G node is the top right of the J node. Current LLMs get this right less than half the time, and these are pretty simple. It's just they're not good at dealing with the spatial relations. And I've found this in a funny way in trying to get GPT-4 to help me draw diagrams. Like if you ask it to draw a diagram of some sort of process, like a genetic algorithm or the accounting process of a business, it can sort of do that, which is impressive. If you tell it, like, draw a box, draw a circle, draw a pointed arrow between the box and the circle, then draw a triangle and draw an arrow from the triangle to the arrow between the box and the circle, like it won't get that a lot of the time. So it's not grounding all this language about boxes and arrows in the boxes and arrows on the screen, even though it can draw these, right? And this is because it's a strange sort of quasi cognitive system. It's not really as human-like in its modes of reasoning and representing as one might think from the somewhat human-like textual responses that it gives. Now, one explanation for the shortcomings of LLMs is that they're just not representing things internally in a reasonable way. What's funny, though, is in some cases they are representing things internally in a reasonable way, but not in every case, right? So there's an interesting system called Othello GPT, where they trained a transformer neural network, the same kind of neural net underlying large language models. They trained a transformer neural network on just a shitload of Othello games, right? And what you find here is not only can it learn to play Othello okay, it's not necessarily the best way to make an Othello playing program, but it's an okay way. But if you probe the internal states of the neural network, right, what you find is you can make a transformation of the internal state of the neural network into features that represent the board state. So I mean, you can mine out of the state of the Othello GPT neural network. You can mine a feature of the form. There's a black piece at this certain square, or there's a white piece at that certain square, right? So just by learning to play the game, it's learning a representation of the board, which it's not given, right? Like it's not given the fact that the board is a square. It's just given neural inputs for each neural net inputs for each square on the board. But it learns that the board is a square, and it learns a nice reputation there. Now, I'm sorry, a nice representation there. Now that it's interesting. It doesn't prove that LLMs are always learning a reasonable representation. In fact, I think usually they're not. In this case, it wasn't few shot learning, right? Like the LLM saw quite a lot of Othello games to induce it to learn this representation, and that's not the same thing as what the LLM is doing when it sees just a couple different examples. Now, I'd like to compare how LLMs work to something called the standard the cognition. So what neural net in a series of tokens, and then some reinforcement learning based on human feedback is used to sort of fine-tune and condition this sequence predictor to do conversations. So people start having conversations with it, then they tell it if it did a good or bad job, and the weights are adjusted by backpropagation based on that. So that's a way to do things, do sequence prediction, do some reinforcement learning on top of that. Now, if you look at the basic way human mind works, it's quite different, right? I mean, we have perceptions coming in, we have actions, stuff we do coming out. We have a short-term memory, aka working memory, which is a memory of stuff we've been through recently. We have a long-term memory, which is, facts and beliefs that we have remembered, life experience we've had. We have a procedural long-term memory, which is stuff that we learned how to do. And when we're reasoning, that's a thinking process going on in working memory, plucking stuff out of these different long-term memory stores accordingly. We then have different sorts of learning associated with different kinds of long-term memory, like one way of learning procedures, which has to do in the brain with the cerebellum, among other parts of the brain. One way of learning new facts and beliefs, which is like an interaction of the cortex and hippocampus. So this sort of architecture is very simple. It's sort of taken for granted in neuroscience or cognitive psychology. Not too much like the ways that you can go detail, you can match to the different features that the cognitive system have to follow this sort of common model of cognition, this standard model of mind. If you do this, LLMs are not the same kind of system. Like they're impersonating a system like this, but they're quite different in nature. Now you could try to make an AI system that works more like the human brain. The best example I know of this is actually happening in Beijing, in China, by a guy named Zheng Yi, system called BrainCog, open source, how the human brain works, and models that can, do concrete tasks like play simple games or recognize stuff in images, by emulating in some detail how different regions of the human brain work. I mean, the open source BrainCog AI system is there, right? So you can download it, you can add on to it, you can play around with it. I mean, it's a valid way to approach AI problems, right? Now, if you don't want to simulate the brain, but you want to sort of improve how LLMs do things, there are ways to make LLMs a little bit more in the spirit of the standard model of cognition, right? So you can try to make LLMs do reasoning a little more explicitly, kind of emulating what the human mind does when it's updating things in its long-term declarative memory using activity in the working memory. So there's a natural program-based deductive reasoning approach, which has been taken with LLMs, where you have the LLM carry out some reasoning, then you try to verify which of these reasoning steps is correct. And if you find something that wasn't correct, you go back and tell them, then it tries to correct what it did, right? And I mean, this sort of feedback it doesn't work miracles, but it certainly helps. And I mean, key to that approach is that you're trying to validate the reasoning that the LLM did with some external verifier, and you're seeing from the external verifier if something worked, and if it didn't work, then you tell the LLM, well this didn't work, and you get it to try to fix that, right? And the Chameleon architecture from Microsoft is somewhat similar in spirit. What you're doing here is you're using an LLM together with some other tools, and the LLM is actually invoking these other tools as needed. So if you want the LLM to say answer a science question and it doesn't know the answer, well, it can search in some special science-oriented knowledge base to find the answer. Or if you're asking it to recognize something in a picture and it doesn't understand pictures well enough, it can consult some image analysis AI method. If you're asking it to solve an algebra equation, it can invoke Julia Symbolics, which is an open source computer algebra system, right? So this sort of approach, it's sort of using the LLM as a common sense interpreter that understands what kind of thing you're asking, and then finds some other tool that's better than the LLM at answering it. And this, in a rough way, is an emulation of how the human mind has many different, subnetworks that are good at different things. And when you're asked a question involving your life history, you're asked a question involving, a fact, then your linguistic cortex may reference different additional parts of your brain to resolve that. Let me just plug in my notebook. So a related approach is self-imitation learning. And again, here you're having the large language model produce answers. Here you're constraining the answers to use a certain vocabulary, which has been identified as a vocabulary within which the LLM tends to make up less BS and make more sense. Then use a separate neural network as a critic. So instead of using an external software tool, using a separate neural network as a critic, then the outputs of the LLM that survive the criticism of that critic network, they're fed back to further fine-tune the neural network. And this sort of self-learning happens in the brain, right? Like when you're being creative, you'll come up with something wild and new and interesting, or complete garbage, right? You don't know. You're just creating stuff, and then you'll go in a different process where you're like, okay, well, was this thing I created that I thought was amazing at the moment, was it actually any good, right? And then you teach yourself that way to create better and better things, so you can imitate this process, which is done in the I2D2 sort of inductive knowledge distillation approach. So these sorts of tricks work reasonably well. They don't bring you to human level general intelligence, certainly. And, the result is when you need to build a practical application using LLMs, in the end, you're often doing something a lot like good old software engineering, right? So for example, Deepmind launched something called WebAgent using LLMs. It's great with it. And I mean, what the WebAgent does is it understands all the HTML code on a web page, and then it can automatically navigate from one web page to the other. So it's an LLM that can use the web, right? It's great. But they didn't make just one LLM here for using the web, right? So they specifically fine-tuned HTML encoders and decoders to deal with the HTML. Then they used another LLM to deal with HTML snippets that are dealt with by these HTML encoders and decoders. And this is a perfectly reasonable way to do it. I mean, you're piecing together some different transformer neural nets doing particular things. I mean, the thing is, the primary neural net based on Google's PaLM model doesn't deal well with the big context size of a huge HTML chunk on a big web page. It deals better with a smaller context size. So you have one neural net that deals with all the HTML on the web page and takes little snippets that fit the context size of another LLM. I mean, this sort of architecture will make sense to any software engineer, but what's interesting is you're still doing software engineering, right? Now, an LLM might even be able to tell you that this is a good architecture to use. It's not yet doing the whole thing of telling you this is a good architecture to use, and then training all the models for you that you will piece together within this architecture, right? So the limitations of LLMs are significant. You can work around them with clever methods, like I showed in the last few slides. In the end, when you're building a practical application, you're still often needing to piece together multiple neural models in fancy ways, or piece together neural models with other bits of code. Now, ultimately, how do we get past these limitations? Ultimately, how do we get from large language models to actual AGI systems, right? Well, I mean, we don't know for sure. We don't know how hard it is or how long it will take. My personal suspicion is we may only be a few years off from real human level AGI. My personal suspicion is we're not going to get there just by tweaking large language models, nor by adding some external resources or critics to them. My suspicion, though, is that you can get there by using a large language model and combining it with some other AI components, and there's a number of ways you could do that, right? So Yoshua Bengio and his student Edward Hu have sketched out one way. They sort of want to combine a large language model with another neural net that tries to learn compact models of the world, sort of a minimum description length learner. So the idea is the LLM is sort of building a repository of surface level response patterns based on the data fed into it, then use another neural network to try to find compact representations of some of these patterns, which will then generalize better because they're abstracting more, right? So this is an interesting approach. It's all neural networks, right? It's all deep reinforcement learning. It's just coupling a large language model with different sorts of neural networks. Now, another approach one can take is one my team is taking in the OpenCog project, and this is all open source software. If you look at the GitHub repository, true AGI-IO, you can find a repository called Hyperon Experimental. And in the Hyperon Experimental repo in the true AGI-IO GitHub, you'll find code that we're building toward the OpenCog Hyperon system, and we're then combining this with other code within the true AGI framework to address enterprise software needs. And OpenCog Hyperon uses LLMs, but they're not the central hub. Like the central hub is something called the atom space, which is a weighted labeled graph or metagraph. It's its big node and link graph that lives across multiple machines in RAM and on disk. And there's types and weights of the different nodes and links in that graph. This graph is called the atom space, the nodes and links being atoms. Then you can represent programs within this atom space. You can represent declarative knowledge, facts, and beliefs within this atom space. You can also represent, whole neural nets or parts of a neural net, like layers of a neural net within this atom space. And we can then connect this atom space with deep neural nets embedded in what's called a neural space, and do hybrid neural symbolic learning. So we're playing now, for example, with having the OpenCog Hyperon system solve math and science problems, by having a large language model take a math or science problem, do what's called semantic parsing, convert that math or science problem into formal logic representation, then feed that formal logic representation into a reasoning engine that does logical reasoning implemented within OpenCog Hyperon. The reasoning engine solves the problem, comes up with an answer in logic form, feeds the answer back into the large language model that puts it into natural language, like English, right? So that's an example of hybridization of a large language model with a logic engine within an integrative AGI architecture, OpenCog Hyperon, to solve problems. And in that way, you can solve some problems that large language models struggle with on their own. You can also use evolutionary learning, like genetic programming, within OpenCog Hyperon. So if you're trying to, write a poem or come up with a new product idea, do something else creative, again, you can ask the query to an LLM, translate what the LLM has read into logic form, feed that logic into OpenCog atom space, use an evolutionary algorithm to combine the logic formulas to come up with some new thing, spit that new thing out to the LLM to put into English. The advantage is an evolutionary algorithm is good at like weird, wild creativity than the LLM is. It can make bigger leaps beyond its training data. So in this sort of approach, you're using the LLM as part of the story, and there are other significant parts of the story. So this is my own approach to AGI. What folks at OpenAI and Deepmind are doing is more like taking the large language model as the hub and trying to add some other things on top of it, whereas here in the OpenCog, we're taking our atom space as the hub and using the LLM to interact with that in a sort of supporting role. Which approach will ultimately get us to AGI isn't entirely clear at this point. It's a research problem, right? So to sum up, really where we are now, I mean, we have some amazing AI tools at our disposal, large language models, other deep neural nets, and other sorts of AI tools as well, like decision forests and logical theorem provers. But we have some amazing tools. None of them are AGI yet. Each of them has significant limitations. If you want to take LLMs and help overcome their limitations in multi-step reasoning or creativity or autonomous agency, I mean, you can do that by various tricks, adding on to LLMs, connecting them with critic networks and external resources. And I've pointed to some projects that are doing that now. From an R&D view, you can also look at embedding LLMs into broader architectures like OpenCog Hyperon. And, these are all really interesting, exciting things to play with. And progress these days happens quite fast compared to in historical eras of AI. And I would encourage anyone listening to this to jump in and help out, right? And in particular, if you want to help out with OpenCog Hyperon and our integration of LLMs with logical theorem provers, evolutionary learning engines, and so forth. You know, there's a Hyperon experimental repository. There's an OpenCog Discord, an OpenCog Google group you can jump onto to connect with people, and there's open GitHub issues you can grab and try to address. So, you know, join the community. The time has come to both use the amazing AI tools available now, such as LLMs, and, you know, work toward the next level of AI, artificial general intelligence, which is going to be even more amazing.